All right. Thank you for inviting me here. Very interested to come back to DDD. I was here several years ago, and I find it a fascinating location to see people really learning from the desert to live in the desert. Right. I'm going to be looking at an arid system, a semi-arid to arid system, and I'll kind of show you the very different dynamics. Doing this work through the NASA LC Luck program that Garrick runs, and working extensively with the American University of Central Asia. So to give you an idea of some of the landscapes here, these mountain pastures, they are snow dominated. Most of the precipitation during the year happens outside the growing season. There's, as you might expect, slope aspect relationships. The outline of the talk, modeling land surface phenologies in thermal time as opposed to calendar time. I'm going to look at the location of montane Central Asia, poised between deserts, the dry, and the higher elevations of cold. We're going to zoom into Naran Rayon, where we're going to model land surface phenologies at multiple scales. We're also going to look at phenometric lapse rates at multiple scales. And then we're going to move to a drier and higher elevation area in Atbashi Rayon to look just at Landsat scale LSPs, and then we'll conclude with some limitations, observations, and ways forward. So what are land surface phenologies? Seasonal vegetation growth and development link the land surface and, of course, the near subsurface with the lowest level of the atmospheric boundary layer, thereby influencing the surface radiation and energy balances and fluxes of water, carbon, and nutrients. Land surface phenologies refer to the spatiotemporal spectral patterns of upwelling solar radiation that vegetated landscapes manifest and observed seasonally using remote sensing. And it's important to distinguish land surface phenologies from ground observations of plant phenologies or crop phenologies, where you have organismal changes that are being identified by their typically structural changes. Land surface phenologies are distinct from, but related to those specific phenologies of plants, and then the much more ill-defined idea of the phenology of vegetation communities. How do you put together all of those things into a coherent set? Well, part of the challenge with the remote sensing is we blur a lot of things, and things that are distinct at the organismal level are obscured when viewed remote sensing. So the fundamental approach that we take is to model a vegetation index, and here we're going to be looking at three different ones, EVI2 and EVI and wide dynamic range, and relating it to the progression of accumulated growing degree days, which is also retrieved by remote sensing. And accumulated growing degree days is just a measure of thermal time that is accumulated above a base temperature. Here is going to be 0 degrees C. We model this as a quadratic function. The reason for that, rather than more complex fits that we might see people doing in calendar time, is that this very simple curve we can solve analytically from for two robust phenometrics, the peak height and the thermal time to peak, using the fitted parameter coefficients for each pixel time series. So we use a bunch of different data sets, VI data sets, Landsat and Venus. Fortunately, we were able to go through the round one Venus competition and get a double scene in Naran Rayon in Kyrgyzstan. That gave us 3 years of excellent data. We're also going to look at the Planet Fusion surface reflectance product that's gap filled. And we also bring in the standard Modus LSP product, version 6.1 for comparison. And then Modus Modus land surface temperature product. We're also going to look at snow cover and the NASA DEM for elevation, slope, and aspect. And there's a bunch of details in terms of model fitting. Won't go into. We see this range of spatial resolutions with Modus. It's 1,000 meters for land surface temperature, 500 for the land surface phenology, and also the snow cover. Forgot to put that in. 30 meters for the Landsat and the NASA DEM, 5 meters for Venus, 3 meters nominally for the Planet Fusion product. There's a variety of study area times, as well as scale at which the temporal scale at which the data are produced. So where are we looking? Here is a GPCC average annual precipitation for the past couple of decades. And in pink, we have the very dry areas. In the cyan, there's that less than 350 millimeters, very close to what Professor Sala was talking about, 380 millimeters per year, and then 400 millimeters a year higher. So the areas that are in black are higher precipitations than this. And we're going to be looking at this area. I focused on 2 ryons, Naren, which is the one that's perched above, and it's a little wetter, and then the larger Atbashi ryon below. Taking a bunch of data through the past couple decades, we produced this map of the average peak vegetation across an area quite a bit larger than Kyrgyzstan. And you're focusing not just on pastures here, but basically anything that is giving us a vegetation signal. Here's a slightly different approach. Instead of looking at the mean by itself, we're looking at the time series statistics. In red, we see standard deviation from the time series. In green, the mean, and skewness in blue. And on top of that, we have quite the outline of the Naren ryon, about 10,000 square kilometers. The Venus tiles are outlined there in kind of magenta, and the Planet Fusion frame, those are 4 tiles from the Planet Fusion product in blue. And then we have a bunch of points that we sampled in 2021. Here are the phenoclimatic gradients for the 21 sites in the Naren ryon. What we see in the upper left is the snow cover annual fraction, the fraction of the year that Modus is showing snow cover on the ground. In addition, our fitted thermal time to peak across those years as a function. All of these are as functions of elevation. We also see over here in the upper right, the 2 phenometrics that we're modeling, and you see there's roughly an inverse relationship up to a point, but as we get above a certain point, it kind of breaks down to a certain extent. Snow cover and the peak height is correlated. Then using the CHIRPS precipitation data set, just focusing on growing season precipitation, I put in a kind of an arbitrary line there of 100 millimeters of precipitation, and flagged of those sites that we sampled, the 2 that had less than, on average, 100 millimeters of precipitation during the growing season. We see one of them at a lower elevation and one of them at a higher elevation. It's contrast with the Atbashi region. So here we have in the upper left the 3 time series, Landsat, Venus, and Planet Fusion. The data that were cleaned, because sometimes you have anomalous high or low values. And then below that are the final fitted time series. We do iterative fitting, and across all of those things, we are putting in overlaying the points, the fitted points from the Modus LSP product. That is a product that uses splines to be able to track what's going on in landscape. And then at the bottom here, we're showing the peak height and thermal time to peak across the 3 years across the various sensors. And it is important to point out that the planet fusion data, we seem to have an extended growing season in these estimates. All of these focused on this one site, about 2,500 meters, subject to spring and fall grazing. And this is a degraded pasture dominated by forbs. We go to a higher elevation site that's summer only grazing. It's also forb dominated degraded pasture. In our approach, if there's not adequate data, we don't get a fit, and that happens in some years. And so at the same time, we can see that the planet fusion data is giving us some interesting and kind of unrealistic profiles, temporal profiles. As we go to various sites at various elevations, we're getting comparable phenometrics. And the one we're most interested in is the thermal time to peak, because it relates to the timing. The peak height is going to vary because we have different spatial resolutions of the imagery. So why do we get this planet fusion extension? Well, it has to do with their gap filling strategy, where we're getting a map here of the day of the year that the time since between the observation they use the gap fill and the day that's filled. And so what we see is these positive increases at the beginning year and negative values at the later part of the year. They're using that within season to extrapolate out. And even down here, they're using gap filling of observations from the previous year. The red lines are plus or minus 21 days. It's clear that this QA information is very important to be able to delimit the time periods that you want to focus in on. The gap filling gives you, and sometimes unrealistic values. So what's a lapse rate? AMS calls the lapse rate as a decrease in atmospheric variable with height, variable being temperature, unless otherwise specified. What we're talking about here is a phenometric lapse rate, which is a change in the phenometric variable with elevation. You're going to get distinct phenometric lapse rates for peak height and for thermal time to peak. And these can co-vary as a function of year, of sensor, of vegetation index, aspect, and slope. Hopefully, they're not completely unrelated to one another. So next few graphs show some PLRs across the common area in the Naran Ryan, where we have the Venus, the Landsat, and Planet Fusion data, and they're all averaged by elevation band. So the mean value of TTP, and then the error bars are plus or minus 1 standard deviation by 100-meter elevation bands. And one of the things that we see is that, again, the planet fusion data are giving us quite distinct relationships across the image. That was for EVI2. If we look at wide dynamic range or NDVI, it's a similar situation. Things are different, but similar. If we go to, if we now move, oh yes, this is for peak height. So in contrast to the thermal time to peak, which we would expect to decrease as we go up in elevation because it becomes cooler, contrast, the peak height is much more stable. Why is that? Well, plants are growing where they're growing. There's a limit at which you start getting significant changes in the vegetation community, but there's much more stability, and that kind of dip in the middle is to do more with the terrain of the area that we're looking at than the ability of the plants to grow there. So we see again in this instance that the planet fusion data are giving us some differences. We get the same kinds of results as we're going across the different vegetation indices. Now let's look at the influence of aspect. So northerly versus southerly aspects defined there at the bottom, again by elevation band. And now we're looking at the northerly minus the southerly difference in the mean peak height. And focusing on EVI2, and the big arrows there indicate the zero line. So below a certain point, we have positive differences, higher peak heights on the northerly side than the southerly side. Then that changes as we get above a certain level. As we look year to year and sensor to sensor, basically the same kind of results, same sort of thing that we see for the other vegetation indices. Now let's look at slope and aspect together. So the y-axes are looking at that aspect difference, and then we're broken down from 0 to 5, 5 to 10, 10 to 15, 15 to 30, and greater than 30 degrees slope. You can see we go from pretty much on either side, and as the slopes are increasing, you're getting an increasingly high bias as a result of aspect. Same kind of thing for the other indices. So let's go back here to the prior lower Apache region, which is about 50%. It's 50% larger and than the areas there, and similar sorts of things, but we have many more rise sites. The kinds of landscape that we're looking at. Lots of patterning in the landscape, sparse vegetation. And going out and sampling, you can see the kinds of vegetation that we get. And over here, multiple years of successful fits within these various sites. But we're only able to successfully fit out of our 20 years, 55%. Some of those are going to, those failures are going to arise from a not enough Landsat data. Some of those arise from weather. Here's another site. Again, different kinds of vegetation, some of it unpalatable, some of it palatable. So let's get down to the kind of the conclusion here. What are we trying to do when we're doing remote sensing of grazed areas? We're trying to establish, are these degraded pastures or these non-degraded pastures? Well, here are 6 different pastures that we sampled in 2021. Which of them are degraded and which of them are not degraded? Are any of them not degraded? You know, a naive approach would be, well, there's more exposed soil, this must be more degraded. More vegetation, that must be better. Part of the challenge that you have in grazing systems is overgrazing can lead to an increase in unpalatable plants that are not eaten, and then they will constitute an increasing amount of vegetation cover and above ground biomass. How do we get at those things? Well, the answer is we need, in addition to the top-down approach, sophisticated understanding of modeling the changes in the vegetation community to be able to link together to be able to identify what is actually degraded from those that are not. So just finally, I just told you all those things, but the basic idea there, we need to move towards land cover quality to link the land surface phenologies to state and transition models to be able to characterize different types of pasture degradation trajectories. And I thank you for your attention. Sorry I went over.
Is any burning question?
Burning questions?
Yeah. Yeah.
Oh, burning questions.
Yeah, I think that we're looking at the personal because
Yep, that's
we
right.
need to go ahead and give the time. So now we have next presentation by.
Morning, everyone. Thank you for having me. I'm a postdoctoral fellow here from the.
Microphone working?
from the Matrani Department of Ecology here at the Lausch Institute. Thank Shimon Rachmilevich for organizing this conference and also supporting this work directly. My co-collaborators Gopal Murali and Uri Roll, also from the Matrani Department. Deserts are diverse and beautiful. They are large and vital habitats supporting valuable human social systems, as well as unique and fragile desert ecosystems. Yet deserts are often overlooked and fully protected. Large gap persists in our appreciation and understanding of deserts, and therefore our ability to manage and conserve them, especially in light of increasing pressures due to increasing global food demands, human land uses, and climate change. And thus my research objective is to assess global dry lands, desert systems, their overlap, diversity, protection, current and future human land use pressures impacting deserts. As I mentioned, deserts are diverse, spread across the world. These include semi-desert steppes, succulent deserts, sclerophyll hot deserts, cool deserts, and hyper-arid deserts. However, a major barrier facing conservation planning in desert regions, the application of different classifications, as desert, dry land, arid, each with different approaches to categorizing desert. For example, we have deserts and xeric shrublands biome as classified by the WWF, drylands as classified by the United Nations Environment Program. We have desert regions as classified by the Global Agroecological Zone. World terrestrial ecosystems as classified by the Nature Conservancy. And these different designations have implications for how we communicate, develop, manage, and conserve deserts. Evaluating these, comparing these different desert designations allows us to highlight the potential complementarity, while at the same time identifying unique desert regions not considered by all designations. Summing these non-overlapping desert regions sum to a combined area of about 12.1 million square kilometers. That's a vast region of non-overlapping desert regions, not considered by all desert designations, that roughly equals about more than half the land area of South America. But of course, these encompass diverse and unique desert regions spread across the world. So from here on, I'll refer to dry lands as classified by UNEP, one of the more inclusive desert designations and often referred to in the literature. They use an aridity index to categorize deserts. That's the precipitation to potential evapotranspiration, basically a measure of the dryness of a region. Subtypes ranging from dry, subhumid to hyper-arid. Drylands encompass about 42% of the Earth's terrestrial surface, supporting almost 40% of the population. As I mentioned, that's a vast and significant region for both people and nature. Next, we compare and evaluate the protected area coverage of drylands by overlaying a map of protected areas with drylands. Drylands are considerably less protected than non-drylands and well below global level targets of protection. Only 9% of drylands are protected, 16% of non-drylands. And this is true across the different desert designations as well. All of them protect only about 9% of their. Returning to drylands, when we compare the protected area coverage of the different subtypes within drylands, we find that not only are deserts less protected than other biomes, the most hyper-arid desert subtypes are the least protected. Comparing protected area coverage across continents, we see that, for example, Asia is underprotected compared to Africa, both of which are poorly protected. These regions are very significant because they comprise a significant proportion of the world's drylands. About 64% of drylands are found in Africa and Asia and are poorly protected. This underachievement of protection targets is important in Africa and Asia, but globally, drylands are underprotected, but especially acute in developing regions, which are expected to develop considerably in the coming decades, but might have a lack of resources or prioritization to safeguarding arid systems. In contrast, Australian and South American drylands are considerably more protected. However, when we consider protected areas that are set aside strictly for biodiversity conservation, we find that an even smaller proportion of drylands are protected, and this is true across continents. The deserts are underprotected. This has important implications for species conservation because deserts are home to many diverse and unique species. Many of them are found in deserts only, and many of them are regarded as threatened. For example, 41% of amphibians in North American drylands are considered threatened. We repeat these analyses for the remaining land vertebrate taxa in drylands for birds, mammals, and reptiles, showing the proportion of each of these in drylands by continent and their threat status. This shows a total number of species of vertebrate species by taxa and their threats categories, and this highlights that reptiles are considerably more diverse in drylands, 481 of which are threatened, and therefore deserve some attention in the context of global levels of protection. Additionally, amphibians are disproportionately threatened, 28% of which are threatened in drylands, and therefore also deserve attention, especially considering that drylands, as I showed you, are poorly protected. And consequently, most desert species have less than 10% of their desert ranges protected. And this is the very minimum for maintaining viable populations. So for example, 94% of reptile species in Asian drylands have less than 10% of their dryland ranges protected. And again, we repeat these analyses for amphibians, birds, and mammals, showing the proportion of species by continents in drylands that have less than 10% of their range protection. And the vast majority of them are underprotected. And this includes a significant number of species with 0% protection and also desert endemic species found nowhere else. Desert species are not adequately protected. Finally, we evaluate urban and agricultural land use pressures today and under different future climate scenarios in drylands. Agriculture is by far the most significant driver of land use change globally and in drylands. These colors show the land use intensity, with darker colors showing a high land use intensity. Numbers in bold show the average land use intensity in drylands by continent. Okay. Next, we evaluate future land use scenarios under different climates and socioeconomic scenarios in 2100. One such scenario is referred to as taking the green road. It's characterized by moderate socioeconomic trends and climate policies, resulting in substantial reductions in global agricultural land. However, such a scenario in drylands would result in a likely increased conversion of natural open drylands, albeit at low intensities, to the conversion of alternative energy sources such as bioenergy and solar panels. And so this shows that even that by 2100, even under optimistic scenarios, majority of open and intact drylands would be converted, especially due to alternative energy sources. This has implications for the future integrity of deserts and desert species, because the majority of drylands are not adequately protected. This shows another scenario. It's an extreme scenario. It's referred to as taking the highway, characterized by rapid and resource-intensive development, high greenhouse gas emissions, and global food demands. As in the previous scenario, it's most of the natural open drylands are converted. Very little natural drylands remain, coupled with a very high average land use intensity across all countries. So the future of deserts is in peril. So to conclude, deserts are large and vital human and environmental systems. A gap persists in our understanding and appreciation of deserts. Different designations comprise broad and non-overlapping based on different approaches to categorizing deserts and implications for how we communicate and manage deserts. Deserts are less protected than other biomes, with implications for conservation and desert species because the vast majority are poorly protected. Finally, deserts face considerable future human land use pressures, threatening the future integrity of deserts. I'd like to acknowledge the Koshland Fund for supporting this research.
Thank you. Time for questions.
I think it would be really helpful to take this analysis and pull together elevation, looking at the mountains and the dry areas, those areas that are kind of dry and snow, and those areas that are hot and dry. Because the biota they're threatened are very, very different. And it would help to make more sense. So you refer everything to deserts, but there are a lot of those areas that people would not consider deserts,
Yeah,
but more dry lands.
right.
So I think there's kind of some mixed messages going on at the moment. You really want to kind of focus down in the most critical areas in terms of risk of change and the loss of
So yeah, in that first sort of chapter that I showed you, that's sort of very briefly trying to make some order of these different designations and exactly how we characterize and define them. Then later in the analyses, actually wrestled with what scale to compare globally. And I could have done it by deserts or by types. There's such a lot of diversity. I could have done it by, I could have separated Gobi Desert and the Sahara Arabian Desert and South American Desert. Ultimately, I decided to just use the spatial scale of continents, scale up to other socioeconomic. The deserts are diverse and they each have biota and vegetation and issues.
If you did it by continent, you left out the driest continent, Antarctica.
Yeah, and Oceania. I don't know two designations that actually consider Antarctica. Not very interested. It's changing and it's present, but personally, I'm not very interested. Maybe other ecologists would agree. But we certainly include the Arctic, and a lot of people would exclude these polar cool deserts. A lot of these designations do, like
scenarios that the dryland region will experience. Did you try to run this analysis scenarios? What will happen in those regions? Because part of it is the fire and large extent they will.
that's something definitely that we've thought about and I've discussed with Baron just over the last few days and with other people, and that's a common question that people ask. Complex, just this was a lot. It's a lot. Yes, that's just definitely something that's interesting, and that's something that I think that could be done simply to project where drylands might be in the future and their level of protection and the species and other pressures. One caveat I would say is that, again, this is how we define drylands or deserts. Dryland is more than just the temperature. It's a product of the vegetation and natural historical factors that define a desert. It's not just the. Yeah, so it's certainly something we thought about, and I'd like to.
Your classification, there is hyper-arid, least protected. I was wondering, what is it to be protected there? Right? For me, hyper-arid is nothing but sand.
Yeah. So, for example, in Australia, most of Australia is desert, and it has a very high protected areas in the deserts. Israel is actually similar, where our deserts have the majority of our protected areas because it's competing for land use space with other human activities. But a desert. So, sorry, what was your question? Why
I showed different degree of aridity,
Yeah.
and then there was hyper-arid, and shows that it was least protected in terms of percentage. And I'm wondering if hyper-arid is just nothing to protect, and that's why it's not protected.
Yeah, well, that's actually the premise. In the first slide was that deserts are actually diverse and beautiful, and the word desert itself is fortunate negative connotation, especially the word desertification. Even the most hyper-arid deserts, and people who live in the desert might know this.
Still have something to
Yes,
protect.
they have very unique species that are found nowhere else, and they're beautiful. They have intrinsic value, and they have ecological value, and they're home to actually people, to social systems at the time.
Hyper-arid areas, they still have.
But yeah, definitely, even in Israel, right?
Israel, I don't consider hyper-arid.
No,
Standard Australia, where it's like
the Aravat Valley is one of the most hyper. It's just 30 kilometers across the valley. It's the most hyper-arid area, one of the most hyper-arid on Earth. Supports very valuable agriculture and it used to support other native habitants.
Anything else? Okay, so we will go to our last presentation by Amir Lausch from Martin Luther University, Germany.
Thank you very much for coming here. I'm not from Halle. I teach in Halle, but I'm based in Leipzig, Environmental Research Center, work at. Presentation is in combination with my colleagues are Jan Humberg and Sam. He's developer of ASIS, and and we want to look on monitoring the global summer bugs. And we know that the remote sensing is really important. Remote sensing create data science or using data science, and also it's ecosystem integrity. It's really important. That's why this was the goal that we developed tool who can manage, quantify integrity indicators different based on remote sensing data, different remote sensing data. This tool you can download from the GitLab now, it's ready, and also the documentation of that. The next few minutes I will explain what we can measure and how does it work a little bit. The ASIS approach, that means trait and trait variation of geo and vegetation diversity can be monitored with remote sensing. This is important. That means we need factual, taxonomic, functional, and temporal patterns and traits what we can measure with such a tool of ASIS. Of course, they are important for ecological modeling and climate change and land use or land use intensity. That's why ASIS is a tool for that we find indicators, quantify indicators, and compare these indicators over the world or between different colleagues. I will explain a little bit what the concept of trait is. Trait and trait variation can or are filters of status, stress, processes, and resource limitations. It means trait and trait variation can be monitored by remote sensing. And for Europe and for Germany, we use plant traits as a proxy of vegetation traits and their interaction with biodiversity. And measure traits, we have different traits here on the top that we have forests, we have buildings, and depending on the process, climate change, land use intensity, you have different land use intensity characteristics. You see that the trait leading to trait variation. Here, that means that we have different characteristics of species composition in grassland or in natural forest or in lead forest or surfaces or cultivated land. That means trait variation leads to a specific spectral response. What we can measure with remote sensing here, really easy NDVI. On the other hand, here, and I will focus on this our test sites, that we can also measure trait of soil characteristics like soil moisture. And here is first look on that. That means that trait of soil moisture can be measured by ASIS. And ASIS quantifies structural patterns, taxonomic patterns, functional patterns, and spatial temporal patterns. Here's a first look on what we did in ASIS. In the middle of that, ASIS as a tool, we are able to measure really these different types of patterns. It's important that we not only have temporal patterns, we have to measure also functional patterns of the systems. taxonomic patterns, and structural patterns. In the future, we want to combine this ACES approach with hydrological catchment modeling. We want to combine individual-based or agent-based modeling called FORMIND set. And also we want to combine with in situ measurement and also with other databases. Here you have one example of spatial pattern classification, or it's not a classification itself. Here you have a look on this patterns, and interesting is that you see this land use intensity in Germany, and you see the border between East and West Germany, depending on the shape and the size of the agricultural landscape. Really interesting indicators for land use intensity. We use time series of Landsat, of Sentinel, or radar data to quantify temporal indicators to integrate it in the modeling. Here you have another example. We quantify based on time series the variance, depending on 30 satellite data. And interesting is here that the light areas, the fields, have a strong change over the time. Dark areas here, forest here of parts, we quantify minor or less changes. Another example is that first slides I showed you the level of raster data, and here we have the second approach that is quantify the zone level. That means in the left picture you see the spectral remote sensing patterns, and overlay of that quantify the zone patterns. It's the zone patterns. It's part of segmentation of this, and here not only a segmentation that you get a vector data set for that. A vector data set integrates different attributes. Here in this right example, you have dendrit, or dendritis. It means you quantify the shape of this dendritis, or you have other examples like diversity and so on. And here in the bottom, you have spectral patterns based on raster data. Another example is that we use indicator of variance to quantify functional patterns. And here you have a look on the middle of this part, because I compare this with Google Earth image. And you see that we are able, or we hope that we are able to quantify indicator or develop indicators which are able to get a realistic pattern of the surface here, so the water content of this region. The first example we have, I will show sensing, or the ACES approach to quantify soil moisture based on remote sensing and in situ data. And this in situ data, they are collected from the mobile cosmic ray neutron sensing technique. This is done from Martin Schrön. And same time we a campaign and also a drone campaign to quantify indicators of region. Here you see the distribution of soil moisture based on this takeover sensing measurements, and we started now to quantify or to get different indicators here soil organic carbon stock, an indicator from digital soil mapping. It's not from us, not from ACES, but it's important for predicting soil moisture. That's why we use that. Second one, we use data from eco-stress sensor, data for transportation for this day, so that we have better prediction based on this data for this. And this is the spectral variance indicators based on the ACES approach for this region. And important is, or interesting is, that we took the data from 10 meters from Sentinel-2, that we have a good solution to quantify these indicators. The overlapping, or the next indicator, was the zone or segmentation of this spectral variance. So to have much more indicators. And here you see the overlapping of the zone over raster data set that we integrate in the model. Here you have a deeper look on this. That you see, okay, we have the raster data and the variance, and then we have also the zone information. Then we got 10 different attributes for each zone. Here is the attribute dendritis, means is the coefficient of zonal perimeter and size for each zone, so that we can have a look if this indicator is important for modeling moisture. Now we started to model and to predict soil moisture, and we integrated different variables, soil moisture, evaporation, different indicators of that. And these are the first results. This is not finalized, but we see that different indicators of ACES have an impact for modeling and predicting soil moisture, so that we can use it for integrated our models. Example 2 is a cooperation or a project. What is doing Martin Schrön and Steffen Zarias from UFZ here with Israel. And Martin Schrön is started to measure soil moisture, water content in the desert with over, and also in the future integrate this sensor type in the train, that we can measure each day, each trail with this technique. Here, I have only this picture because these results are not published yet, so that means I can only show you this. That means that this experiment and this approach from Martin Schrön and here can be really interesting, and also the combination to quantify different potential indicators, combine and predict soil moisture based techniques, forest techniques. Okay, these are some references for my work. Normally, I work sensing to understand forest health, and I published also monitoring biodiversity with remote sensing, so that you can have.
Thank you, Kendra.
You mentioned new technologies. What exactly are those?
Technology?
New. So there's new technologies to measure the soil.
It's not a new technology. I'm not an expert of this measuring, this cosmic ray. You mean that? Or you mean the ACES?
Oh, this is the new technology. There's nothing added to this. There's nothing new aside, like this is the new technology or.
No, the ACES technology is new, it's really new. Peter Selsom worked since 20 years or 30 years sensing, and he developed this, started developing years ago. Now we integrate much more good indicators and try to find out which indicators are interesting for modeling species distribution, soil moisture, or land use intensity, depending on the patterns, on the functionality of the traits, surface, and this.
Are you using quantum computing? Oh, is quantum computing starting to sensing world for you? I mean, quantum computing?
Not yet, because his approach is really fast. And we have a small application, region in Germany. But when we need more power, then it can be that we quantum computing. Depend on now we integrated Sentinel Lancet data, but also we can integrate hyperspectral data, and then the spectral information is much more stronger than other systems, and you have to use quantum.
Other questions?